All right, welcome back, everybody. Statics class, snow day. So glad you all got to sleep in. Hope you're all safe. We got nothing out here in the south part of the Portland metropolitan area. I'm in Malino, kind of Beaver Creek area. It's cold, really cold, but we got no snow. And must be high elevations, must have some stuff. The only thing I can think of, but we got to keep moving forward. So this is going to be a little lecture on frames. I would like you to review the lecture on method of joints for trusses. And I'd like you to review the lecture on method of sections for trusses. And practice. That would be my key. Practice and come with your questions on Wednesday. Because we recorded everything, I don't need to give you another lecture on it. I think that's all right there. You just need to watch it again and practice. I'm going to do frames now, and then we'll have that done. And then chapter 5 is pretty done. We got to get kind of bump chapter 6 and maybe 7. We can do 8 next term, and then rock and roll on 9. So we do got to keep going. I haven't posted anything for homework today, but I'll be giving you a frame, so look for that. And then we'll meet in person on Wednesday, March 1st. So, okay, now let's do some frames. Oh, kind of forgot where I'm going here. All right, so I have this set up. This is number 40 out of the book. And first, let's identify it as either a truss or a frame. So is it made out of triangles? Yeah, kind of made out of triangles, except for this tall thing. That's definitely not a triangle there. So are all the loads at the connections? Connections are A, B, and D. There's no connection here. There's just an external load. A, B, and D, are all the loads there? None of the loads are there. This is up here at C, and this one is here at the midpoint of member AB. So we do have straight members, that's good, but it's definitely not a truss. So we need new logic for that. Actually, the new logic is not new. We have the logic already. It's equilibrium. We have a new strategy though, new starting point. Actually, not even that. Step one is still free body diagram. What does that mean? Free body diagram? That means take out the supports. That's a pin at D. So I take that out and I put in what? 2 reactions, and I guess, right? I'm going to say up for dy, and I'm going to say to the left for dx. So step 1, free body diagram, take out the supports, whatever they are, and put in the reactions. That was also a pin. So I'm going to say this goes down because this is trying to pull it over, right? The whole thing's trying to rotate. So I think AY's got to hold down. And then on the X, don't know. I'll just put into the left to help fight that 600, okay? So here's the key. Take out the supports, put in the reactions, but do not take the frame apart yet, okay? Leave it together and try to get as many reactions as you can. Frames are unique in that often they're pin-pin, which gives us 4 reactions. So that's problematic in statics because we have 3 equations in statics. Forces in the X equals 0, forces in the Y equals 0, and a force in the moment, and the moment equals 0, not force in the moment. And the moment equals 0. So that tells you right away, if it's a pin-pin system, that you probably won't be able to get all the reactions, but get any that you can get, okay? How do we get them? We apply our equations, and it's, if we can think about it before we actually write the equations, that's helpful. So if I think about summing forces in the X, I have 1, 2, 3, and how many unknown? 1, 2 unknown. So that equation is not going to give me anything. It's going to give me 2 unknowns. If I sum forces in the Y, I have 2 unknowns. Those two. I have 1 known and 2 unknowns. So neither one of those equations are going to help me. Excuse me. That means a moment. If I can sum a moment at a point where 3 of these things drop out and I'm left with 1 unknown, then I can solve for something. So let's see. If I sum the moment at A, what drops out? What forces go through point A? Well, obviously AY and AX, they're gone. They do not participate in any rotating about point A. It's like the finger on the door hinge. Nothing happens. DX travels also right through A. So DX drops out. So that's the harder one for students to see. But it's true. It goes right through the point. So it does not create moment. DY creates moment. So does the 400, so does the 600. So let's do that. I'm going to write it up here, giving myself a little more space. Some moment about A. And I'll just start with the 400 times 3 feet. And that rotation is negative, clockwise. And then I'll do the 600 times its distance to A. So again, here's its distance, looks like 8 feet. And its rotation is also negative. And then dy times its perpendicular distance, 6 feet, and its rotation better be the other way, plus, and set it equal to 0. Okay, so moment about A gives me 1 unknown, that's good. And it's giving me positive numbers, that's good, because these two go positive when I move them over here, correct? All right, so then dy is going to equal, and I can just crunch it out here real quick. So that's that one, and then that's that one. I'll add those together because they both move over here. And then I'll divide by the 6,000. And it came out positive, so dy points up. Remember that positive sign just says, yep, you guessed correctly. It doesn't say that dy points up. It says that dy is correct, the right direction. All right, so now that I know I got 1,000 going up and 400 coming down, I need another, how much coming down? Yeah, another 600, because these two are going to add up to 1,000, and this one is 1,000. All right, so I was able to get both of the y forces, but I cannot get the x. There's nothing I can do. I can't take a moment somewhere. If I did a moment up here, they both produce, they're going to be both in the equation. I'm stuck. So that is frames. You often cannot get all the reactions, okay? With trusses, we can always get all the reactions, typically. I guess I shouldn't say always, but 99% of the time, okay? With frames, it's the other way around. 99% of the time, you cannot get all of the reactions because often it's pin, right? All right, so what do we do now? Because we still want to know what's going on here. And then the question also is what's going on at B. They're going to want to know that at all the connections, right? Just like in trusses, we want to know what's going on in all the connections sometimes. So to get that, it's now time to take it apart. So with frames, we now take it apart. So once you have gotten your reactions, then take it apart. And that literally means take it apart, right? So I'm going to separate member CBD into its own free body diagram, CBD, and I'm going to put in what I know. I know dx is unknown, and I know dy equals 1,000. Okay. And same with AB, member AB. I'm going to draw it separately, and I'm going to put in what I know. So I know that AY is 600, and I know that AX is still unknown. Okay. So we take it apart. Now, when we take it apart, we have a little more to do, because now you've removed a pin, right? B was together, up there, together. And when you take it apart, we have to put in forces for that pin. Pin gets how many? Yep, it gets 2. So you can do it on either member, whatever you want to do. I would do it on this member because my 2 forces this way are known, right? And my 2 forces this way are going to be known. So you can put it in however you want, but since these 2 are going down, this one has to do what? It has to go up, by. And then I'm assuming AX goes that way, but I don't know that for sure. So that means I got to put BX, because when I'm doing this, I'm just looking at this piece in equilibrium, right? Just that piece. So if just that piece is in equilibrium, then these 2 have to oppose each other, and these 3 have to balance out. It's equilibrium, right? So I made the guess. Now, in the matching point at B here, I have to make it opposite, because when these come back together, that pin's got to be in equilibrium. BX and BY. So once you make the assumption on direction here, you have to be equal and opposite here. In other words, BY and BY, same magnitude. BX and BX, same magnitude. Okay. And now you look at it and go, okay, which half can I focus on and find something out, right? If I look at this, I have a couple unknown in the X, but I only have 1 unknown in the Y. BY needs to equal what? By some forces in the Y, I have 1,000 up, and I have BY down. And that's got to equal 0. BY has to equal 1,000 pounds, right? Every member's in equilibrium, stands on its own. But if I found out BY here, then I transfer it to here. 1,000 pounds, right? And then this should work on this side. Let's look at the Y forces. 1,000 pounds up, 400 down, 600 down. 1,000 pounds, balances out. That's good. All right, we still don't know these 2, and we still don't know these 2. So now what? I get some forces in the X, but that gives me 2 unknowns. Yep, you're right. Some moment. So let's do it, and I'm going to work with this right side, because this is a vertical member. It's going to be easier. This is an angled member. It's going to be more difficult, and there's more going on. So this is pretty straightforward. A moment about, if I choose here, these 2 drop out, and I find BX, right? So I'm going to do that. Some moment about D, right here. BX times what? 6 feet. And that rotation is counterclockwise positive. And then the 600 also creates moment. So 600 times 8 feet. Good. And the rotation, negative. How about the BY? Does it create moment about D? No. Go straight through the point. That's it. Set it equal to 0. BX equals. I'm going to do this first, 600 and the 8 times, and that's going to go over here and become positive, and then I'll divide by the 6. 800. And it's easy to tell, and that becomes positive, so this BX is 800. Right? And that means my direction is good. It is that way, right there, BX. All right, and that means that this BX is also 800. And it must point this way, and then that means, since these are the only two, looking at this side now, these are the only two, right? In the X, AX must equal 800. So there we go. All of it solved. I know everything down here, X and Y. I know everything here, right? No, I haven't done this one yet. So back over here. I know I got 800 here, and I got 600 here. What's DX got to do? 800 to the left, 600 to the right. This direction is incorrect. Now I could write that out, but I think you guys at this point can see that conceptually. 600 to the right, 800 to the left. I need another 200 to the right. Now it's solved. Everything at point D, everything at pin A, and everything at pin B. I can now design it with strength of materials. So frames. Step 1, free body diagram. Step 2, reactions. Step 3, take apart. Step 4, work individually, work each member. Okay, so a little cookbook for frames. You could write a little cookbook for trusses, method of joints, and you could write a little cookbook for trusses, method of sections. But now we have frames. So, all right, I hope that helps. And I will be giving you a frame project to work on, and we'll make it due on Wednesday. Come with your questions, review the lectures on sections and joints, please. And let's rock and roll chapter 5 out of here. All right, stay safe, stay warm. See you Wednesday.